Hey everybody, welcome to astronomy. Hopefully the video started right there, not a few seconds ago when I was swearing at my microphone because things weren't working. I think I got everything straightened out now. We're going to talk about the planet that we missed, or the not a planet that we didn't talk about because it's not a planet, and that's Pluto, and all the way out to the outskirts of our solar system. And then we'll be done talking about the stuff that orbits around the sun. Until the late 1990s, early 2000s, this was the best photograph we had of Pluto and Charon. We could barely see any detail at all. In the late 90s, the Hubble Space Telescope started making maps of the surface, what they think the surface was, just based on the fact that the brightness of Pluto and Charon changes slightly as they rotate. So they were able to figure out that like there were dark patches and light patches on it. So this isn't exactly a photograph. It's more a brightness map of how the brightness has to change in order for them to change in brightness the way they appeared. So early 2000s, this was the best idea we had of what Pluto and Charon looked like. They're really far away. The inner part of their orbits around where Neptune is, the outer part goes all the way out to 50 AU away from the sun. Here's another sort of brightness map showing we were pretty sure that there were variations of brightness of the surface because as it spins, we could see those, but we couldn't really take a clear photograph of it until we actually sent a space probe there. That space probe was called New Horizons, and this is a photograph of Pluto and Charon taken as the New Horizons spacecraft approached the pair out there at the edge of the solar system. So our understanding and knowledge about Pluto has increased 100-fold in the past decade or so. One striking feature of Pluto and Charon, you can just look at it and see how similar they are in size. Pluto is on the right here, Charon is over here, but Charon appears only to be like about a quarter of the size of Charon only appears to be about a quarter of the size of Pluto. So they're much more similar in size than any planets in the regular part of the solar system. Because of that fact, when we think about something orbiting like a moon orbiting a planet, we picture the planet staying still and the moon going around in a circle, right? But that's actually not what's happening. The planet and the moon orbit the center of mass. But for a planet like the Earth, which is big, and our moon, which is really, really small, the Earth only moves a tiny, tiny bit as the moon moves around in orbit. But Pluto and Charon are so similar in size that Pluto actually moves in a sizable circle outside of its own radius as Pluto. So Pluto and Charon orbit around their mutual center of mass, and that motion of Pluto is visible. That's actually how we discovered that it had a moon. Excuse me one second. I don't know if any of you have allergies, but the pollen right now is destroying me. The other thing that's interesting about Pluto and Charon, we talked about the fact that tidal forces can lock an object's rotation. So for example, our moon's rotation has been slowed down by tidal forces to the point where one side of the moon always faces the Earth. Pluto and Charon have slowed down each other's rotation. So one side of Pluto always faces Charon, and another side of Charon, and one side of Charon always faces Pluto. They're always facing the same sides towards one another. So if you went to Pluto and you went to the other side of Pluto, you would never know that Charon existed because it's only visible from one side of the planet, the side that faces Charon. And if you went to Charon and went to the other side of Charon, you would never know that Pluto existed because you always face away from it. So they're always facing the same sides towards one another, and that's called tidal locking. We've talked about that before. Here is a lovely picture of Pluto from the New Horizons spacecraft showing, I think, a much more interesting surface than anybody predicted. I think people sort of expected Pluto to be an icy moon with not a whole lot going on. But if you look at Pluto, you can see that there are different kinds of terrain. There's some impact craters, but not as many as you would expect, which, remember, we've said this many times, anytime an object without an atmosphere doesn't have many impact craters, you have to guess that, well, there must be something kind of eroding them over time. And what could be eroding craters on Pluto? There's no atmosphere, there's no wind. What's going on here? When we look at this photograph, we can see that it looks like, if you look over here, it kind of looks like mountains, right? Just like rocky mountainous terrains. By the way, Pluto's composition is largely icy, not rocky. We know the density of Pluto, and we know it's much, much less dense than rock. So Pluto is a mixture of ice and rock. It's one of the reasons we don't classify it as a terrestrial planet. Terrestrial planets like Earth, Mars, Mercury, Venus are rocky. Pluto is not rocky. It's icy, largely. But then there's this very smooth layer of ice here that almost looks like it's overlapping over top of that mountain. In fact, it looks like here that these mountain peaks are kind of poking through this layer of ice. And there's evidence from looking at the ice on Pluto that it almost looks like dunes on the Earth, that this ice is maybe moving across the surface, driven by the heat of the sun, which there isn't much heat of the sun, way the heck out in the outer reaches of the solar system. But that this ice is maybe melting and periodically refreezing, and that leads to it sort of creeping slowly across the surface. By the way, this ice is not, I mean, there's some water ice, but it's not primarily water ice. When we say ice in astronomy, it could be any frozen thing. This is actually nitrogen ice. You know that nitrogen is what our atmosphere is mostly made out of. You may have seen scientists do demonstrations with liquid nitrogen, which is what happens if you get nitrogen 300 degrees or so below 0 Fahrenheit. This is solid nitrogen. If you keep getting nitrogen colder and colder and colder, it will freeze solid. So the ice on Pluto is solid nitrogen, and it looks like it's actually slowly kind of creeps across the surface and then gradually covers over the mountainous and crater terrain. We can see craters over here in this part of the terrain, but this smooth ice is gradually covering over those craters, which is pretty cool. Pluto does not have what we would call an atmosphere per se, but there's this word that we invented, and I think we talked about it when we talked about Mercury as well, to describe a very, very, very thin envelope of gas trapped by a planet. This is a photograph of Pluto backlit. So New Horizons has passed Pluto. It's looking back towards the sun. So we get to see the edges illuminated by the light of the sun. And we can see there's a little glare there. That light is reflecting off of something or passing through something and lighting it up. What is that? That is what we call Pluto's exosphere. It's a very, very thin envelope of gas, very tenuous, quote unquote, atmosphere that's less than 1/100,000th as dense as the Earth's atmosphere. So very, very thin, very, very little gas, but gas nonetheless. Nitrogen gas, some methane, carbon monoxide, and so on. So some bodies in our solar system, even little tiny ones like Mercury and Pluto, have a very, very thin, tenuous envelope of gas trapped by their gravity, very kind of close to the surface, but much, much less dense than what we would call a proper atmosphere. But it may be that the motion of this very tenuous envelope of gas over the course of millions of years is enough to kind of erode the shape of these glaciers and kind of mold them into moving dunes that creep across the surface of the moon. Here's a close-up of Pluto's largest moon, Charon. A couple of interesting features. Notice that there's kind of evidence of past geological activity, things that look like rifts or mountain ranges, a kind of lowland terrain down here and highland terrain up here. Lots of craters covering the surface. And this reddish brown stain of these tholins, these organic goop of simple organic molecules, chains of carbon atoms and hydrogen and nitrogens, that are the result of simple organic chemistry involving things like methane and carbon dioxide, forming more and more complicated organic molecules. We see it all over the place in the outer solar system. The other thing to notice about Charon is you can look at it and tell that it's not quite round. Charon is right on the border of an object that's big enough for its gravitational pull to fully squish it into a round object. You can see here at the poles, it's kind of lumpy. The gravity isn't strong enough to squish those high parts down and make the moon completely spherical. The object in the solar system that Pluto and Charon are most similar to is Neptune's moon Triton. If you look at a picture of Triton, it's easy actually to mistake it for Pluto. You've got your rocky terrain, you've got your what looks like ice that's kind of flowing over top of it. And this leads astronomers to suspect that Pluto and Charon and Triton are all similar sorts of objects with a similar sort of history. Remember, we said that the other weird thing about Triton, this is Neptune, and this is Triton. Triton goes around Neptune in the opposite direction from almost all the spins in the solar system, the spins of the planets, the spins of the planets' orbits, the spins of the moon's orbits around their parent planet, all in our solar system are pretty much in the same direction, except Triton goes the wrong way. When we talk about how the solar system formed, that requires an explanation. It would be weird for one object in the solar system to form moving in the other direction from everything else in the solar system. What we think happened is that Triton was an object that lived out where Pluto and Charon live, that veered into Neptune's orbit and got grabbed by Neptune's gravitational pull in the wrong, just grabbed it from the backside and spun it around in the wrong direction. So Pluto and Charon and Triton make a little family of icy, small, moon-sized stuff out at the edge of the solar system. There are other little moons in the Pluto system. Pluto has Charon as its big moon. It's here on the bottom, it goes off the screen, but it also has little moons, kind of Mars, the size of Mars's moons, these little, kind of potato-shaped, irregular, a few miles across moons, Hydra, Nix, and Styx, and Kerberos. Here's a scale here, that's 10 miles. So Nix is about 20 miles, 30 miles the long way, and maybe 50 miles. Sorry, 20, 30 miles the short way, maybe 50 miles the long way. Styx and Kerberos are less than 10 miles across. We get to Pluto and we feel like we're at the end of the solar system, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto, is it a planet? Is it not a planet? By the way, why don't we want Pluto to be a planet anymore? It's because it is not rocky. It is icy. It's because it has a wacky orbit that actually comes inside of Neptune's orbit and goes back outside of Neptune's orbit, and is also tilted a large amount to the plane, the flat plane that defines most of the orbits in our solar system. And the fact that it doesn't seem to have fully cleared out its neighborhood of the solar system. We've mentioned many times now that Pluto lies right at the inner edge of a region of the solar system that we call the Kuiper Belt. And the Kuiper Belt is a region of our solar system filled with kind of leftover junk from the formation of the solar system. Ice crystals and dust crystals from the size of snowflakes and grains of sand up to things the size of ice cubes from your refrigerator and gravel from your driveway, up to the size of things the size of cars and houses, up to things the size of, well, Pluto. What we consider Pluto to be nowadays is sort of the innermost Kuiper Belt object, the innermost large Kuiper Belt object. There's a collective term for these large, well, there's actually a few collective terms for these. What do we call Pluto now? If it's not a planet, we call it a dwarf planet. Another name for Pluto, that was about its location, we call it a trans-Neptunian object, which is the big fancy way to say it's some crap that's out further away than Neptune, right? There's another name for little objects that are kind of like Pluto. And some astronomers call these Plutinos, meaning like little Plutos. But there's all kinds of junk out here. And remember, we're at a 50 times the Earth-Sun distance, so 50 astronomical units across the Kuiper Belt. Out beyond the Kuiper Belt, extending thousands of astronomical units into space, is a sphere of material orbiting the sun, the size of grains of dust, grains of pollen, literal snowflakes. And this material slowly orbits the sun. It could take 100,000 years for a snowflake out here in the Oort cloud to make a single orbit. So the edge of the solar system is fuzzy. It doesn't just stop. The Kuiper Belt is out there. It's thin and gets thinner and thinner and thinner. The Oort cloud is out there. It gets thinner and thinner and thinner. And there's no hard edge to the solar system. In the past 20 years or so, we have discovered that the Kuiper Belt is filled with objects that are as big as or nearly as big as Pluto. The first one discovered in 2003. 2003, UB313 was initially named Xena. The name was officially given Eris in about 2010 or so. And Eris is further away from the sun than Pluto. It's maybe as big as Pluto or almost as big as Pluto. And we started finding more and more and more of these things. So that's when we invented the category trans-Neptunian object to just refer to any big icy body, bigger than a comet, but smaller than Pluto or around the size of Pluto, that's out beyond Neptune. Because we realized at some point, look, if we call any Pluto's sized round junk out there a planet, we're going to wind up with 30, 40, 50 planets in the solar system. And nobody wants that. Nobody wants to make elementary school students memorize the name of 45 planets, right? So we decided enough's enough. If it's icy and small and out beyond Neptune, it's a trans-Neptunian object. We lump all those things together into this category. Eris is actually bigger than Pluto, we think, about 1.5 times larger than Pluto. Its orbit takes it out almost 100 astronomical units from the sun. That's almost twice as far away as Pluto gets from the sun. So it's way the heck out there. And we now know Eris has a little moon of its own. Maybe it has a name. I don't know Eris's moon's name. We have also discovered an object a little bit smaller than Eris called Sedna. We've also discovered an object a little bit smaller than Sedna called Quaoar. So here's the Earth, here's the moon, here's Pluto. Eris is bigger than Pluto. Sedna is almost as big as Pluto. Quaoar is a little bit smaller than Pluto, but a little bit bigger than Charon. As of, I think this is as of 2017 or so. Dysnomia is the name of Eris's moon. Eris has a moon called Dysnomia. We discovered Makemake. We discovered Haumea, which has a little moon called Namaka. Haumea is not big enough to be round. It's kind of oblong. By the way, most of these are not, in fact, none of these are photographs. These are all artist conceptions. These are just paintings of what these things could look like. We don't, when we discover them, they're just the tiniest of specks in our telescopes. There's Quaoar again, 2007. OR1 didn't even have a name yet when this slide was made. Orcus, which has a small moon called Vanth. There's all kinds of junk out there beyond Pluto, orbiting in the Kuiper Belt. And this is just the big ones that are bright enough, reflect enough light that we can see them in our telescopes. There's hundreds, surely, of objects the size of Dysnomia, Nix, and Waywatt, and these little moons of the trans-Neptunian objects. A more recent one has Salacia in it. And this is from a few years later. Again, this to give you scale, the Earth is here, the moon is here. So these are all smaller than the moon. But they're all almost as big as Pluto. So if you want Pluto to be a planet, it would be super unfair of you not to want Eris to be a planet and not to want Sedna to be a planet, not to want Makemake to be a planet. So either there are 8 planets in the solar system and Pluto and all this other stuff is something else, or there are 20, 30 planets in the solar system, and it's going to keep changing every couple of years as our telescopes get better and better, and we discover more and more of this weird little stuff out in the Kuiper Belt. Here is a picture of all of the biggest Kuiper Belt objects discovered to date. There's Pluto and Charon. There's Triton, Neptune's moon, which notice how similar it is in size to Pluto too. Here's Ceres, the biggest asteroid or dwarf planet, if you want to call Ceres a dwarf planet, which I think most astronomers do nowadays. Here's our moon, here's Mercury, and here's all this various stuff out in the Kuiper Belt. Some of it didn't have official names when this slide was named. It just has a year and a number designating what number of things was discovered. So a lot of them like the size of Texas. There's Texas. Quaoar is a little bit bigger than Texas. This one's about the same size as Texas and so on. And I think this drawing, I thought this drawing scrolled down. Oh, I've got my slides mixed up. Let me go back up. Okay, so as of now, we probably know of 25 or so large Kuiper Belt objects. We will almost certainly discover more in the next few decades. There are some astronomers who think there might be something as big as Mercury out in the Kuiper Belt, but it's 200 AU away from the sun, so it's so dim that it doesn't reflect much light. We haven't seen it yet. There are some astronomers who think there might be something as big as Mars out in the Kuiper Belt that we haven't discovered yet. Do we call that a planet? Who knows? These categories don't mean anything, right? They're arbitrary. These are just balls in space that we've decided to put them in different buckets, but the names of those buckets and where the dividing line is between, oh, these are dwarf planets and these are real planets, that's just a human construct. It doesn't mean anything. Here's a map, a graph, a chart showing every dot represents some object in space. The horizontal axis is how far away we are from the sun. The vertical axis is how tilted the orbit is of the object from the flat plane of the solar system. The orbits of Saturn, Uranus, and Neptune are shown here: 10, about 9.5, a little less than 20, about 30 astronomical units from the sun. So the number on the top here is the distance in AU from the sun. The yellow dots are asteroids that venture out into the outer solar system beyond the orbits of Saturn, Uranus, and Neptune. Here is Pluto. Pluto's orbit is about 30 to 50. Pluto is, its orbit is very elliptical, so sometimes it's close to 30 AU from the sun, but sometimes it goes all the way out to 50. So that circle represents Pluto. That's Makemake. That's Haumea. That's Orcus. And you can see all these other blue dots are other trans-Neptunian objects, but there's a bunch of them in Pluto's orbit. You see this concentration of Plutinos, little bigger than Comet, but smaller than Pluto objects that orbit in the vicinity of Pluto's orbit. And this goes all the way out. Eris is way out here, almost 70 AU away. And so, yeah, there's a high concentration here, but fewer out here. You might say, does that mean that this part of the Kuiper Belt, 50, 60, 70 AU from the sun, has fewer objects in it than this part here, 30, 40, 50 AU from the sun, where Pluto is? Maybe it means that, or maybe it just means that this stuff is so far away that it's hard to see, so we haven't discovered them all yet. This is something that's really important in astronomy, not to give too much meaning to what we haven't seen, because that could just be an artifact of what's easy to see and what's hard to see. You might say, oh, well, we look at this graph, we see there's lots of stuff here where Pluto is, and lots of stuff a little after Pluto, and then not much stuff out here. So that means there's not much stuff out there. Well, maybe it just means that stuff that's much further away than 50 AU is so dim that we haven't discovered it yet. So that stuff is there. We just haven't seen it yet, so we can't put it on our graph. This graph, though, this chart diagram, does capture the idea that it seems like the Kuiper Belt kind of just gradually fizzles out. And so there's a place where it's most dense just outside the orbit of Pluto. And then the stuff gets less and less and less dense as you go further and further and further out. Why is the Kuiper Belt interesting? Why are trans-Neptunian objects of interest? They're just all kind of rocky, icy balls, right? They're just, why is that exciting? Why do we care about ice balls at the edge of the solar system? Well, the reason that trans-Neptunian objects, Kuiper Belt objects, are of interest to astronomers is that these objects have probably not changed at all since the solar system formed 4 billion years ago, 4.5 billion, almost 5 billion years ago. You pick up a rock on the Earth. That rock has been through geological processes and chemical processes. It's been, it might have been a mile underground 1 billion years ago, being crushed by the heat of the Earth's interior, and erosion and plate tectonics brought it to the surface. All of the minerals and rocks and substances on the surface of the terrestrial planets have a long and complicated chemical and geological history. All the stuff at the edge of the solar system, these little tiny balls of ice and rock, probably have exactly the same chemical composition and the exact same physical structure that they had 4 billion years ago. So the material in a Kuiper Belt and the material in the Kuiper Belt objects out there is like a time capsule from the formation of the solar system. If we could scoop up a bunch of junk from the Kuiper Belt, that would be like scooping up the original nebula out of which the solar system formed. So in order to understand the early processes, the early mineralogical processes that led to chemical elements coming together to form rocks and minerals in the first place, we have this place we can go in the solar system. Now it's hard to get there, it's far away, right? But we have this place we can go in the solar system that has this sort of pristine original material that was the raw material that the solar system was formed out of. And it's still out there, orbiting right where it was when the inner solar system started to collapse under the force of gravity and clump together into planets and into a sun in the center. All of this stuff in the outer edge was just moving too fast to ever clump together, and is still out there orbiting exactly the way it was orbiting 4.5 billion years ago. So that's why the Kuiper Belt is interesting. Yeah, it's cool that there are these icy planets out there that are super far away from the sun, and they're all a little bit different, and they're all a little bit unique. And that's interesting from just a factual point of view to know that those things exist. But from a scientific point of view, what we could learn from studying these Kuiper Belt objects is we could learn something about the chemistry, mineralogy, geology. It's not quite the right word to use until the planet actually forms, but I think you know what I mean. The early history of the material that was the raw material out of which the planets and solar system originally formed. Okay, so that's why the Kuiper Belt is interesting. And I bring that up because if you choose for your NASA mission assignment to do the mission that is exploring Pluto and Charon and then continuing out to orbit a Kuiper Belt object, that's why the Kuiper Belt is interesting. That's why objects in the Kuiper Belt are interesting to us. Okay, I will stop there. Today is Thursday. I'm recording this on Thursday. Friday, I'm going to do two things. I'm going to post the lab for Friday, and I'm also going to record a short lecture about the sun, so that the following week we can talk about nuclear fusion. We can talk about stars in general. We can talk about stellar evolution. I'm going to try to get through that part of the class really, really fast because we are still kind of behind. I want to make sure we have at least 3 weeks to talk about cosmology and the Big Bang and stuff like that. So we're going to put our foot on the gas next week and try to get through stellar astronomy as quickly as we can.